Introduction to second-order non-homogeneous differential equations. Recall that homogeneous linear differential equations has the form of Ly equal to 0 for some linear differential operator L. So when this right side is 0, you call that a homogeneous differential equation, linear differential equation. For example, here's y double prime plus y equal to 0. This is a homogeneous linear differential equation because the right side is 0. And you can set a linear operator L as d squared plus 1 and rewrite the differential equation as Ly equal to 0. Now, why is that same as this? Well, try this out. D squared plus 1 applied to y. When you apply d squared and when you multiply by 1, it's d squared y plus y, and it's same as y double prime plus y. Therefore, Ly equal to 0 is same as y double prime plus y equal to 0. Now, what's the significance? Well, if you have two solutions, f of x and gx, satisfying Ly equal to 0, then by linearity of L, the linear combination is also a solution, because if you apply L to c1fx plus c2gx, that's c1 times L times f of x, and c2 times L times g of x, and then you also know that right here, L of fx, this is equal to 0, and L of g of x, we know that it was a solution to Ly equal to 0, so this is also equal to 0, and 0 plus 0 equal to 0. So what I'm trying to say is that if you have a homogeneous differential equation, which means the right side is 0, then the linear homogeneous differential equation has a solution written as a linear combination of many solutions. Okay, now what's the difference between this and the non-homogeneous differential equation? Well, non-homogeneous linear differential equation doesn't have a 0 on the right side. Here's an example, y double prime plus y equal to 1. To see what's the difference, let's just use the operator L equals to d squared plus 1 again, so that the linear differential equation is now written as Ly equal to 1. Then, let's say you have, again, two functions f of x and gx as solutions of this, meaning that if you apply L, you're going to get 1, which is on the right side, and L of g of x is again 1, same as the right side. Look what happens if we operate L to the linear combination of the two. Well, same as before, L gets multiplied to f, L gets multiplied to g, so you have LF and LG, but these individually, aren't these equal to 1, and this is also equal to 1 now? So C1 times 1, C2 times 1 is C1 plus C2, and unless C1 and C2 are some specific values, it's not going to give you 1. So this is the big difference. The big difference is that no longer you can take many solutions and take linear combinations to produce the general solution. Okay, then what do we do? Let's try to investigate this simple non-homogeneous differential equation for a while. Here are some observations. Y equal to 1 is a solution. Why is that? Well, if you take 1 and differentiate twice, because it's a constant, all the derivatives are 0. So this becomes 0 when you plug in 1. 1's second derivative is 0. When you plug in 1 into y, it's 1, and 0 plus 1 is indeed 1. So y equal to 1 is the solution to this equation. Now, another observation is that had this been a homogeneous differential equation, meaning that this 1 is 0 instead, then we know this differential equation. This is a differential equation. If you put the y to the other side, we know that it's y double prime equals to negative y. So we're looking for functions whose second derivative is negative of itself. We did this before. We know that such functions are cosine and sine. So the solution is y equal to c1 cosine x plus c2 sine x. In the operator notation, this is what it means. L of 1 is equal to 1. So we're using the same operator, d squared plus 1. Applied to 1 is 1, because 1 is a solution to this differential equation. But if you apply L to c1 cosine x plus c2 sine x, because this is a solution to Ly equal to 0, it's going to produce you 0. Now let's use that awesome property of the linearity again. So let's see what happens if you apply L to the sum of the two. Well, if you apply L to the sum of the cosine, sine, and 1, then you can split this into L applied to the first part, cosine and sine, plus the second part, L of 1, because of the linearity. Linearity means that you can split additions and differences, and also any constant multiple, you can pull it outside. That's what linearity means, right? So you know that the first one produces 0, the second one produces 1, and 0 plus 1 is equal to 1. Okay, so above calculation shows that C1 cosine x plus C2 sine x plus 1 satisfies L of y equal to 1. In other words, this is a solution to y double prime plus y equal to 1. Now, if this operator notation L is a little confusing, you should try this on your own. So try this. Take this, differentiate it twice, plug it in here. Take this and replace the y, add them up, and see what you get. You are going to get 1. Okay. Alright, in the previous solution, y equal to 1 is called the particular solution, while y equal to c1 cosine x plus c2 sine x is called the complementary solution. Particular solution is just one solution that satisfies the differential equation, and one satisfies this one, right? So it's just one of the many possible solutions. That's what a particular solution is. On the other hand, the complementary solution is the solution of the homogeneous differential equation, the equation that you get by setting the right side equal to 0. So complementary solution is the solution to y double prime plus y equal to 0. Now, if we have a particular solution yp and a complementary solution yc, then the general solution can be written as y equal to yc plus p. Why is that? Well, that's because if you apply L to yc, that just becomes 0, and L applied to yp produces the other one that you want to produce. So, since L of yp is 1 and L of yc is equal to 0, when you apply L to the sum of them, it produces 1, and therefore it's a solution to, the sum is a solution to L of y equal to 1. Not only is this c1 cosine x plus c2 sine x plus 1 a solution to this equation, it's actually a general solution. It's the general solution because it has two free parameters. So if you had two initial conditions, you can set up these c1 and c2 values so that it satisfies the differential equation completely. That means this is all possible differential equation solutions that you can imagine. It's the general solution. Okay, so here's the plan for solving a linear non-homogeneous differential equation. Suppose we have a differential equation ay double prime plus by prime plus cy equal to fx. I just made this simpler by making a, b, and c as constants, but same steps can be used even if these are not constants. But because those are much harder, we will limit our discussion to the case when these are constants. So let's say you have a constant coefficient second order linear non-homogeneous differential equation. Then here are the three steps you must take. So first, find one particular solution yp of the differential equation. How this could be done will be shown to you in the later videos. Now, step 2 is to find the complementary solution, which is the solution of the differential equation where the right side is set to 0. Okay, and then you add the two, the complementary plus the particular. That will be the general solution. So this is the general scheme of things when you solve a non-homogeneous differential equation. Let's do one final example. Y double prime plus 2y prime minus 3y equal to e to the negative x. Now, think about the differential operator on the left. What is this? This is two derivatives, d squared, twice of the first derivative is 2 times d, and it's a multiplication operator by negative 3, so you put negative 3. What function will produce e to the negative x that's on the right when L is operated? That's basically the question, right? If we can solve that, that gives us a particular solution. Well, try this first. If you just casually apply L to e to the negative x, then all this computation leads to negative 4 e to the negative x. Now, this is just a very simple calculation that anyone can do. But notice how the final result of this calculation is so close to e to the negative x on the right. In fact, the only difference is you have this negative 4. So do this. If you take this L and apply it to negative 1/4 e to the negative x, and you see the purposes of this negative 1/4, right? Because by linearity means this constant multiple can be pulled outside, so this is pulled outside, and when you apply L to e to the negative x, we already know that it's going to produce negative 4 e to the negative x, and therefore when you cancel the negative 1/4 with negative 4, you get e to the negative x. What does that tell you? It's a solution of L of something equals to e to the negative x. Therefore, this is a particular solution to the above differential equation. Okay, this idea will be studied further as something called method of undetermined coefficients. But for now, I just wanted to show you how once you get the particular solution, you can use the complementary solution to get the general solution. Okay. All right, now let's go for the complementary solution. The complementary solution is the solution to the homogeneous differential equation, which means you put 0 to the right, you write down the characteristic equation, solve it, you get 1 and negative 3, and it gives you this. And then finally you say the general solution is the complementary plus the particular, and this is the answer to the differential equation. So that's the general solution. Now, to reiterate the idea of the linear operators further, think of it like this. L applied to this, this complementary solution gives you 0 because it's the solution to this differential equation. It creates this 0, okay? L applied to this particular solution gives you e to the negative x because it's the solution to this equation. Therefore, when you add them up and apply the L, when L operates in the first two, it gives you 0. When L operates the second part, this negative 1/4 e to the negative x, it produces e to the negative x, and therefore at the end of the day, it produces e to the negative x, which means this thing inside here is the solution to the above differential equation. And since it has two free parameters, we know that we have a general solution in our hands right now.